Yes.
Audio
अब ये
कौन
लाइव
सा?
टा शेयर कर दूँ मैं। ଏବେ ଦେଖିଲ ହେଉଛି ଲିଙ୍କଟା ପଠେଇ ହ୍ୱାଟ୍ସଆପ୍ ଯାଇକି ପଠେଇ କପି କରୁଛି। ଆରେ ଏଠାରେ ପଠେଇ ଦେବି। डिलीट कर दो।
चलो स्टार्ट।
स्टार्ट
Shadigan? Okay. Very good afternoon, you all, and we are going for advanced data structure. And in today's video, we will be covering the singly and doubly linked list, and mainly we will be covering the things like this. First of all, what is this singly and doubly linked list? What are the use, where you use, what is the terminology we will be using here, and what is the implementation details, and how we can insert element, how we can remove elements, and the complexity analysis, and the code implementations. These are things we are going to cover today's thing. Let us start with this singly linked list. You can see it is just a sequential list of nodes. The circular part, what you see, these are the nodes containing data. So one node is linking to another node. You can see it is just given an arrow mark like this, or which points to other nodes. This first one also contains data, next one also contains data. So what are the use of this linked list? So in many area we'll be going for these things. Especially we'll be going for using list, queues, stack implementations. Then creating circular list also we'll be using. There are so many things I have given here. You can even for implementation of adjacency, list for graphs, we can use all the things, right? What are the terminology we'll be using here? Basically, four terminology we'll be using. One is the head, that is the starting point to the starting node here, and one is the tail at the end. You can see here, and one is the pointer. It is referring to another node. So this circular is one node. This is another node. One pointer is there. That is the pointer. And node, you can see this is a circular thing like that. It contains some data. Okay. So these are the terminology we'll be using. Now, let us see the difference between the singly and the doubly linked list. In the singly linked list, what we see, it only holds a reference to the next node. That means from 3 to 84, only one link is there. You cannot come back to 3. Okay. From 84 to 85, 85 to, you see one arrow is only in one direction, it is going. And the reference is to the head. The starting is the head, and the last one is the tail, like that. While you are going for the double linked list, you can see so there is arrow to both sides. That means 15 it points to 6, and 6 also points to 15. Like that, both side it will be there. And the double linked list is to do quick additions, removal from both the ends. Okay, that is the advantages of singly double over the single linked list. What is the pros and cons? If you can see, and the single linked list, it uses less memory. That is the pros in a single linked list. But in double linked list, it can traverse backwards. Also, it travels in one direction, single linked list, but in double linked it can go for in both the directions. Then what is the cons? It cannot easily access previous elements. In case of single linked list, we cannot access the nodes of the elements of the previous one. The another thing is that the double linked list cons is that it takes twice the memory. See what is the memory it takes for single linked list, twice the memory it consumes. That is the things. While coming for the implementation, let us see a single linked list. So nodes are there, 5 containing 5, 23, 7, and 13. The head is pointed here at 5 and tail is at 13. Now I want to insert 11 for the third node. So from the, you can say this is the first, second, third. So how do you do all the things? You see, so the while you go for the traversal, it is the first, it is the second, and third. Okay, in the third, I want to insert 11. How do I insert 11? You can see it here. For inserting 11, what I need to do? First, from 11, we give a pointer to 7. From 11, because before 7, I want to insert that one. From 11, I give a pointer to 7. And from 23, next one you see, from 23, I just give a pointer to 11. So then it is successfully inserted. Okay. Now the traversal will be gone. So this is gone. Similarly, suppose I want to insert 11 where the third node is. See, this is the double linked list. Previous case you have seen, if you see here, it is only in the single linked list I am inserting 11 in the third. In this case, it is a double linked list. I want to insert 11 in the third. What is the third one? First node containing 5, second one is 23, third one is 7. So in the seventh, just before that, I want to add this 11. How do we go for that one? So this is the first one, traverse first one, second one, third one. Okay. So third one, I want to insert 11. I put the 11 here. Now what I need to do, from 11, I put a pointer to 7. Okay. And similarly, from 23, from 11, I put a pointer to 23 also. Okay. Then what next I have to do? See, this node, what was that 7 to 23, that will go from 7 to 11. And what was 23 to 7, that will go to 11. You see the next one, I'm putting it like this. The next step, put it and traversal, so it is gone. So you have seen how I have inserted in the single linked list and how I have inserted in the double linked list. Okay. Similarly, suppose I have to remove from single linked list. Any say suppose I want to remove 9. Where is 9? So first, second, third, fourth. From this 9, I want to remove from this single linked list. Also, similarly, we will try to how to remove from the double linked list. Okay. So traverse 1, 2, traverse 1, 2, traverse. So I want to check it where it is there. Okay. Now I find 9 is there. Okay. Then what you put it in the temporary temp. Okay. This I want to remove. If I want to remove, then what I have to do? So I have to put an pointer from 4 to 15. Say from this one to this one. Okay. This I have done. I put traverse that one and I put a pointer from 4 to 15. Okay. Then the next step, what I do? This temporary it is gone. Now, if you see, then I have successfully removed the 9 from this one. Now all the traverse is gone. So head and tail it is there. Same thing, I want to remove 9 in a double linked list. 9 you can see with the first, second, third, and fourth. Go on doing like this: first one, second one, third one, and fourth one here. So this 9 I want to remove. Then what you have to do? The similar things what you need to do. So first of all, you have to put a pointer from 4 to 15. 4 to 15, because I have to remove this one. Then in this case, what I have done, what are the pointer? It was there from 4 to 9. If you see the previous one, a pointer was also there from 4 to 9. This one I removed, this pointer. Instead that pointer I'm putting 4 to 15. Next, what I've done, so I also removed the pointer from 15 to 9. That also I disconnected this one. Okay. The next step, what I do, totally remove 9. Gone. The next step is that. So like this, I can go for adding in the single linked list, removing in the single linked list. Similarly, adding in the double linked list and removing in the. Then while you go for the complexity analysis, because you know that two type of complexity, the time complexity and space complexity. So we mainly worried about the time complexity here. The searching in the single list is order of n, and the double list is also order of n. So insert at head it is order of 1, and it is also order of 1, and insert at tail also it is order of 1 order. This I am talking about the single linked list, double linked list. There is no much difference here, right? But while we are going for this, removal at head, for the single linked it is order of 1, so it is also order of 1 double linked list. But removal at the tail in the single list it is order of n. Here it is order of 1, and removal the middle also, both the cases it is order of 1, order of n. Okay. So these are the things. Now another linked list we come across, that is a circular linked list, and it is a linked list where all nodes are connected to form a circle. Okay. There is no null at the end, and a circular linked list can be single circular linked list or a doubly circular linked list. Okay. So you see this shown like this, you can also put in a circular manner like this. Okay. So from this is the element it contains 2, and there is a pointer from first to second. So from second to third, from third to fourth, and the last one there is a pointer from the last to the head one. Only we see a pointer at the head remaining there as it is. Okay. Then what is this advantages of the circular linked list? You see, any node can be starting point, because there is no starting point here where it starts, where it ends. You cannot, because anywhere you can start, anywhere it can end. So any node can be a starting point. and we can traverse the whole list by starting from any point. We just need to stop when the first visited node is visited again. Okay, where you started, you have to end there. Second thing, it is useful for implementation of queue. Unlike these implementations, we don't need to maintain two pointers for front and rear also. If you use a circular linked list, and we can maintain a pointer to the last inserted node, and front can always be obtained in the next. Okay. So these are the things we studied about the linked list. The next one we will be going for, as I promised you that we are going for the binary search tree or the binary tree. Okay, just 5 minutes. 5 minutes. 5 minutes. So, okay, coming.
Yes.
How many people are there? Like,
Four, five.
oh, request them to join more people. Now, the next part we'll be discussing about this binary trees and binary search trees. Okay, so outline is like this: what is a binary tree, and what is the use where you use the binary tree, and what is the binary search tree, and what is the complexity analysis. Okay, so then thing is that how to insert nodes in the binary search tree and how to remove nodes on the binary search tree, and also binary tree traversal. Three things are there, as you know: pre-order, in-order, and post-order, and the level order transfer, and also a glance at of some source codes, right? Here, we can have some terminology. A tree is an unidirected graph, as you can see. So direction is only one direction. A tree is a sorry. A tree is an undirected graph which satisfies the following definitions. What is that? An acyclic connected graph. There is no cyclic there. It is not closing. Okay, and there will be n number of nodes and n minus 1 number of edges. So for example, if I consider a tree like this 405, so nodes are 1, 2, 3. So 3 minus 1, 2 number of edges are there, like that. So how many number of nodes are there? If the number of node is n, then edges will be n minus 1. Okay, and graph is a graph in which any two vertices are connected by exactly one path. Then coming to the root nodes, here we have a rooted tree, then we'll not have to reference to the root tree nodes. So this is the root of this entire tree. Okay. Similarly, if you see the child is a node existing from another node. See, if I say this is a child 2, node is 2, it is existing from this one. So if I say 3, it is existing from this one. If I say this one, it is existing, it is coming from this one. Okay. Then what is the parent of a root node? Or if this is a root node, there is no parent of this root node. Okay, so that you have to remember. Then child node, it is extending from another node. A parent is the inverse of this one. Say suppose 0 is a child node, it is extending from this parent node 4. Okay, so if you see it here, 0 has 2 children. What are the children? 0 has 3 and 2. These are the 2 children, and 0 has 1 parent, that is 4. Right. So similarly, a leaf node is a node with no children. See, I say 3 is a leaf node here, it has no children. Here 2 is a leaf node, it has no children. So what are the things it is coming in, say, yellowish or brownish color? So these have no children. Okay, that's why I call them as the leaf node, right? Then another thing is that subtree. See, if a tree is containing another tree, so the entire thing we call it as a subtree. Okay, we'll see the example what is the meaning of the subtree. So if you see I am explaining the third one. So this is just like this one. That means it is containing one node and one tree. So again in tree there is containing another 3 trees. This is one tree, this is one tree, one tree. So if you go on expanding, so it will be like this. Okay. Then if this is the tree, then what is in a binary tree? A binary tree is a tree for which every node has at most 2 children. Remember, not at least. So a tree can have only one node also, but it should have maximum 2 child. If it is more than 2, it is not a binary. Binary means 2. Okay. If you see this example, so this is a binary tree. The root node is 1. It has 2 children, 5 and 0. Similarly, if you see this is a binary tree, the root is 6. For this 6, 2 children, 0, 8. For this it is 5 and for this one it is 1. It is saying maximum it should be 2. Okay. Now let us see this example. This is also a binary tree, is a tree for which every node has at most 2 children. Here you see all the cases maximum 2 children are there. But if you see some cases, is this a binary tree? Now you can answer yes. For this it has 2 nodes. For this it has maximum 2 nodes. For this it has 1. It is okay. For this it has 2, for this it has 1. So no here it is exceeding 2. That's why it is a binary tree. Yes, it is a binary tree. But in this case, is it a binary tree? You see, for 1 it is okay. For 7, it has 3 number of nodes, 3 number of children. So it cannot be a binary tree. So answer is no. Okay, no, this is not a binary tree. Similarly, is this a binary tree? See, if this is the root node, it has 1 less than 2. 1 has 1, it is also less than 2. 0 has 1, it is also less than 2. Yeah. So this is a purely binary tree. We don't have any problem. Yes, this is a degenerated one. Your people not attending this live session. Then the question comes, what is a binary search tree? Okay, binary search tree, it is also a binary tree that satisfies the BST invariant. What is the meaning of that one? The left subtree has smaller elements and the right subtree has larger elements than the node. Try to understand these things, what I'm telling you. Take the middle one. The root node is 2. So what is the nodes left to this one? This is 1. 1 is less than 2. Then what is the node right to this 2? It is 3. So 3 is greater than 2. So in this case, it is a binary search tree. If you see this one, this is also a binary search tree, because a binary search tree by default it should be a binary tree. In a binary tree, what is the condition? It should have at best 2 nodes, at best 2 children. Okay, so 8 has 1 child, 9. So it is the right side of 8, it is 9. Similarly, right side of 9 is 11. This is also a binary tree and it is also a binary search tree. This is also a binary tree and this is also a binary search tree. Coming to this one, so suppose I start with 8. So to the left it is 6 less than 8. To the left it is 2 less than thing, and also to the right is greater than 2 but less than, sorry, greater than 6 and also greater than 2. There is no problem on that one. Coming to this one, so this 9 is greater than it, because the right hand side should be greater than, and to the left it should be less than 9, the same time it should be greater than 8 also. Okay, so as it is satisfies all the 3 diagrams what you have seen, these are the binary search tree. Okay, so let us see, is this a valid binary search tree? What we find, you see, the root node is 3 and the left child is 3. It is a case of not less than, it is equal to. Sometimes we may accept it is a binary search tree, or we may not accept also, depend on the condition. Okay, there written, it depends on whether you want to allow duplicate values. In that case only, if you allow duplicate value, it is a binary search tree, otherwise no, right? So it is a valid BST, you see. So 4 is less than 5, up to this it is okay. Here 7 is greater than 5 and 6 is also greater than 5, it is up to okay. Yes, it is a binary search tree. It satisfies all these conditions. Yes. Let us see whether it is the A, B, C, D. It is not necessary that always numbers will be there. Even if character we can put here D. C is before D and A is before C, it is okay. And Y is after D and X is before Y and Z. Yes, it is also a valid binary search tree, right? So like this we can put it. Now we are going to check whether this is a valid binary search tree. Let us see. See, this is 4. I take the, what is the root node? Root node is 5. So 4 is less than 5 and 1 is also less than. 8 is greater than 5 and 7 is also greater than 5. 6 is also greater than 5 and 7 is less than 8 and 10 is greater than 8. Here 6 is less than 7 and 9, it is purely BST. Is clear? Yes. Oh, sorry. What is the, let me check it. So here it is saying it is 9. So 9 is greater than 8. 9 it should, because whatever the elements, it should not be greater than 8, because this is existing to the left side of 8. So all the elements should be less than 8 only, because 9 is greater than, it won't be case, right? So is this a valid BST? Now sir has to answer. Nicholas, is it a binary search tree, BST? Is it a binary search tree? Any of the students can answer? No. Why? No. Because it is cyclic is there. One cycle is completed there. It should not be there. Okay. If at least you remove one arrow here, then it will be BST. Okay. First of all, I need not check all the numbers, only because it is cyclic is there, so it can be BST. So this is the things you have seen. Is this a valid BST? You see, 20 is greater than 1. So it is up to this. And 19 is less than 20 and greater than, it is okay. And 2 is also greater than 1 and also less than, it is okay. 3 is greater than 2 and also less than 20 and greater than 1 also. So 18, 11, 17. So it is a purely BST. Yes. This is a structure satisfies the BST invariants. Okay. Now, what is the binary search tree? What is the invariants? What are the things are there? So implementation of some of the map and the entities, and while you are going for the red black trees, while you are going for the AVL trees, the split trees, etc., we'll be using the BSTs, right? So using the implementation of binary heaps, the syntax trees used to compiler and calculator also will be using the binary search tree, and also for the tree a probability data structure uses for randomization of this BST, right? So if you see the complexity, it is the at best we are going for the O order of log n. You can see the O of log n. It is log 2 base 2, not 10. Then average cases O log n for all, and for worst cases order of n, right? So you go for the insert, delete, remove, and search. It is the same. Then the next thing we'll try how to go for inserting elements to the binary search tree, how to delete or remove. Okay. Let us start here. Now I'll take the help of some students, and they will tell me insert 7. So I inserted 7 first. 7 is there. Then I have to insert 20. So this 20 will be right side of 7 or left side of 7? Yes, it will be to the right side. It's clear. So now I inserted 20. Next is 5. So this 5 will be to the left of 7 or right of 7. 5 is less than 7. So it should be to the left of 7. So I put it 5. Clear? Then is 15. 15, you see here, 15 is greater than 7, obviously, and 15 is less than 20. So it should appear here. Okay. So you go for this one, this one, this one, and left up it is 15. Then I want to insert 10. So 10 is greater than 7, it should be in the right hand side. 10 is less than 15, so it should be the left side of this 15. Same thing we do it here. Is clear? Then I want to insert 4. Where you put 4? 4 is less than the root node 7, and 4 is also less than the 5. So 4 must be to the left of 5. Okay, same thing we do it here. So yes. Then insert 4. So it is a duplicate, so we cannot insert that one. It will not allow duplicate things, so it will stop you, right? So it's we have encountered a value that is already in the tree. So if your tree supports duplicate, then only you can take it. Otherwise, it is not possible. Okay. But the next one, you want 33. Where you put 33? 33 is greater than 7. It should be to the right side. 33 also greater than 20. So it should be to the right side of the 20. Okay. Insert it here. So here it is 33. Next is insert 2. Where 2 comes? So less than 7, less than 5, less than 4. It should come to the left side of this 4. Okay. Same thing we do it here. Yeah, it is 2 there. Next is insert 25. 25 is greater than 7, greater than 20, but less than 33. Less than 33. Okay. So in that case, it should come somewhere here, right? So now go on doing exactly. You got 25. Next I want to insert 6. Next I want to insert 6. Where you can insert 6? So 6 is less than 7. 6 is less than 7 and greater than 5. Okay. Then if you see it must be somewhere here, right? The same thing I am doing it here. Is it clear? Now on average the insertion time will be logarithm of that one, right? So now suppose I want to adding element to a binary search tree. Same thing what we have practiced there. I am doing it here, but you see it here. It is a very tricky question. Sometimes you get these questions in the GATE exam also. So first I put insert 1. I added 1. So 2 is greater than 1. It should come to the right. So 2 is here. So 3 is greater than that one. It will come right to that one. So 4 is greater than 3. It will come right to that one. And 5 is greater than 4. It will come right to 4. And 6 is greater than 5. Also, it will come to the right of that one. So this is the binary search tree. Fine. So this type of linear behavior is very bad, and it is the reason why balanced binary search tree were invented. Okay. So then suppose I want to remove a element from the binary search tree, what do we do? Okay. So let us see the example why we started here. Find a page, find queries, find 14. Where is 14? I have to find it. So 14 is less than 20. So we must come to the left hand side, and 14 is greater than 10. It should come to the right hand side, and 14 is less than 15. We should come to the left of this one. See, left of 15, it will come to that one. It is 12. So it is greater than 12. So it should come here. So 14 is there. So we found that one. Okay. You see the process. So first we see I have to find 14. So it is I started with the root node that is 20. It should be less than 20. Come here. It should be greater than 10. Come here. It should be less than 15. Come here. It is greater than 12. Clear? You found that one. Next, find 25. Then start that one from the beginning. 25 is greater than 20, and less than 31, so you got that one. Similarly, I want to find 37, right? So 37 is greater than 20, start here. It's greater than 20, greater than 31, less than 42, greater than 35, so 37 got it. Suppose I want to find 17, it is there or not, I have to check it. 20 less than, greater than 10, greater than 15, 19. So 17 is not found. So it is saying at this point we discovered that 17 does not exist in this binary search. Fine. So in the removal phase also 4 cases are there. So node to remove is a leaf node. Then how to remove a leaf node here? Node to remove has a right subtree but no left subtree. And this is the things I think we can take in another video. Thank you for watching this video. If you have any query, we are free. You can ask some questions. Otherwise, we'll end this session here. Thank you. Thank you once again for watching this video. Good. कौन कौन कलम देखा